Structuring systems, an application of structural modeling, basic structural modeling. This is part 4 of this series, and of course this is our introductory series. This series of videos will be reworked later on around the first of the year as we go forward and continue to improve this particular set of information. So as shown in the introductory video, this is my website. If you click on this particular link right here, and on the website there's a tremendous amount of background information and also the charts that go along with this particular video. This is my Twitter feed, and I announce new videos, new information there, and you can also ask questions or send me messages there. So the overview, basically go through a little bit of introduction and the fundamental concepts and the general process steps. This particular set of information we've gone over a few times in the videos before, so I'm just going to hit the highlights going through at this time. General process steps, I'm going to talk about those a little bit more in detail. We've added more information in the third set of steps that we go through. And then we'll go through the process steps a little bit, stopping with process step number 7, and then leaving the final process for the next video, which would be part 5. So overview of the slide content. Basically, I'm going to present the basic concepts and ideas that drive this approach. And what we're doing is we have a conceptual type of design process that we're going through here, and we're looking for a conceptual solution to this set of problems we're discussing. So what we have is we have 19 cities that are in an unordered state. We really don't have any information about them except that we know they're cities and they're related to each other in some way, and then we go through and we order those using this process that we're designing here. The general process is known. What we're designing is the software to support it. So the 19 cities are in an unknown, unordered state, and we take 5 cities and we select those at random. We do that first. Then we select empirical data for each of the cities that we have randomly selected, which of course gives us 25 empirical data points. So we actually know the cities, and then we go collect some data about the cities. But then we use inference in this process to reduce the amount of effort it takes to collect data. So we're really integrating 2 types of truth here. We're integrating empirical factual truth, and we're integrating logical or formal truth through the inference, and the inference step can be computed and allows us to reduce the cost of collecting the empirical data. So then after we do that for the first 5 cities, then we collect 5 more cities. We get 5, then we get the empirical data for those, and this second set of 5 cities is what we've added the material to today. We'll talk about that a little bit more in detail. Then we order those cities, and this ordering process is the subject of the computer code design. So this is what we'll be talking about today. We'll introduce some of the detailed mathematical operations that may be candidates to reduce to computer code, and then of course we'll perform the inference operation. Now the inference operation was basically put together as a proof of concept by Warfield, and we have, and prior to developing these videos, we've used the Sage math tool to compute the inference operation. But when this goes to code, then we may have to change that, but we also may be able to do the whole proof of concept code in the Sage tool. In fact, that will probably be the first cut process that we do for the open source software, is to actually create Sage code to demonstrate this process. Then there's 5 more cities, and these cities basically are selected one at a time for the highest inference potential. We then order those after we get 5. We'll talk about those more in the next video. And then again, as I said, we select the city with the highest inference potential, gather empirical data about that city, order the city based on the new empirical data, and then perform the inference operations. And what this does is, after we get a large enough set of known information or inferred information, then we can go through and say, instead of selecting cities at random, then we can select the city that gives us the highest payback for the amount of effort we're going to put into collecting that empirical data, or gives us the highest return for that data. And that, of course, is going to be the city that gives us the highest inference potential. And designing that inference potential is also part of this process that we will have to figure out how we're going to do that in code. So the fundamental concepts here, there's basically three types of truth: formal, factual, and value. And create an approach that uses the same computational system. And the authors have developed the abstract relation type, which integrates truth operations all in the same type of framework. Marking space supports formal and factual truth. The value space supports value truth. And of course, what we're doing is we are structuring the system using its components. And these particular processes are fairly fundamental, but they're not necessarily integrated within the computing aspects, because formal truth and factual and value truth have separate types of operation, computer type of operation systems. Formal truth has its type of logical computing approach with Prolog and other types of common logic operations. And factual and value truth, these are usually statistics and real numbers and integers, countable numbers. So what we do is we integrate these operations all into the same type of number system and then compute from there. And of course, the types of truth, again, we have the formal truth, the factual truth, and the value truth. Now, systems engineering is over here in the value area, where we're trying to create the most value for society by solving problems in a manner that optimizes the value to the society or the group. And the primary purpose, one of the primary purposes of this activity, is to actually take things that are known by experience, which is factual truth, take this factual truth and combine it with formal truth in a way that reduces the cost of actually finding the information and doing the optimization. And of course, as we see here, when we start mixing these, that formal truth is not known by experience. Factual truth is known by experience. Value truth, of course, is sometimes yes, sometimes no. And are they certain? Formal truth definitely is certain. Factual truth is not. So when we start mixing these, we start getting a kind of a blurred line between these aspects. And if it's important in any one area of your computation or your problem solution to know more about these, then that would be a different type of analysis that you would do in those steps. The abstract relation type, which was created by the authors, basically has three spaces: marking space, outcome space, and value space. These specific spaces can have multiple matrices in each one. Here we only show multiple matrices in the value space, but you can have multiple matrices in the marking space, and also have multiple matrices in the outcome space. The abstract relation type essentially works on a model exchange isomorphism, which basically is the idea that you have three representations of the same information or the same model. You have a prose description of the model, a graphic representation of the model, and a mathematics or computer representation of the model. This isomorphism says if I have a mathematics and computer representation of the model, I can change it into a graphic representation and have the same identical model with no loss of information, or I can change it from a graphical representation of the model to a prose description of the model again, without having any loss of information, have the same model. So this gives a way that you can go through and represent the same model in 3 different ways. This really helps because if you're communicating to a large group of people, which you're normally doing in systems engineering and systems science, then you can show the same model in these 3 different forms and different. Some people are good with mathematics, some people are good with graphics, other people are good with prose, and so they can figure out the best way that they know to get this information where they can understand it. Then of course the 3 different models reinforce each other. A person who understands mathematics may get insights from the graphics. A person who understands the prose may get insights from the graphics. And the abstract relation type basically requires that you document the abstract relation type in formal prose. You can also have informal prose, and then you give the representation of the model itself in the graphics and also in mathematics. And system structure and components, primarily what we're saying here is that human beings usually use the system concepts in 2 different modes, design mode and discovery mode. And most of the graphic representations that are used within systems engineering and systems science are really in design mode. They are graphic representations that are used to communicate a design. In this particular case, we're in discovery mode, and we are actually using the graphics to communicate the developed structure or the developing structure of the system. So we're actually going through in a stepwise fashion discovering the structure of the system. So we know the objects, we know the cities, but we really don't know the relationships between each city. So we're going through and we're using these graphics and prose and mathematics down here in the discovery mode, which again is a little bit different than most of the typical applications of of graphics and mathematics and prose, and especially in systems engineering, because you're usually using prose to document your design, using graphics to communicate your design, and you're using mathematics to essentially discover or verify or optimize your design. So again, we are down here in the discovery mode, we are not in the design mode. System structure, and we define a system as a relationship mapped over a set of objects. So we know the cities, those are the objects. We know the general relationship is north of. But we must discover the specific relationship between each city pair with incomplete information about each city. So we have an unknown type of ordering, and then we have incomplete information about each city as it relates to all the other cities, which is an analog for many real world situations where you really kind of generally know what's going on, but you have to go out and discover the specific relationships between each object. So the general process steps, of course we're going to identify the cities and create the initial matrix, and then we're going to collect and enter the initial empirical data, analyze and order the cities. We've gone through this before. Conduct the inference analysis. Last time we went through some of the mathematics on that. Then we're going to collect in additional empirical data, analyze and order the cities again, and then conduct inference analysis. Step 7, this is where we'll stop this time in this particular video right here. And these, of course, if you click on these, they will take you to those parts of the presentation. So here's our beginning configuration. We know we have 19 cities, the yellow zeros and the red zeros. So the 0 with a yellow background means it's unknown. We really have no information about that, either up here or down here. A 0 with a red background means that it's false. So the way you read these is city 2 north of city 1? Well, there's a 0 there with a yellow background, which is unknown. We really have no information about that. We haven't collected any specific information on the cities yet either. So when we look at how do we know that these the zeros on the diagonal are false. Well, let's read it. So is city 1 north of city 1? Well, logically, just from formal logic, we're not going to allow a city to be north of itself. So we know that that's false. So is city 7 north of city 7? No, we're not going to allow that. So every diagonal red is false. All of the other cells in this beginning configuration are yellow because it's unknown, and with a 0 in it because we really have no idea, because we haven't collected the empirical data yet. So now what we do is we go and collect the empirical data. You select the 25, we'll select the 5 cities at random, and then we select the 25 data points, or 5 data points for each one of the cities. And that green 1 means that's true, and a red 0 of course means that's false. So let's read this. It says, is city 2 north of city 1? That's a green 1. That means yes, that's true. We know that's true. Is city 1 north of city 5? Yes, that's a green 1. We know that's true. But in this ordering process, which is the subject of the design of this operation, what we want to do is we want to move all of the green ones down to the lower triangular. So we'll go through, and what we do is we swap we swap the rows and columns to move the green ones down into the lower triangular. So now we're going to swap column 14 and 11. Here's 14 and 11 has been swapped. Now let's see. Now we're going to swap rows 4 and 10. So here's rows 10 and here's row 4. Now we're starting at the top, and what we did was we swapped row and column 1 and 2 right here. We start with this 1 right here at the top, and we swap that out. So now that 2 is at the top, now we're going to go, let's take a look at 11 and 2 and see what 11 and 2 looks like. It's 11 and 2. Now we have 11 at the top, there's nothing there. So the next one we're going to look at is 1 and 2, see what that looks like. Right there. Next one we're going to look at is over here. This is 15 and 10, so we're going to look at this one right there. Well, we did actually, 15 and 15, and there's 10 and 15. So we did 10 and 1, and then 10 and 6. As you can see, we're starting up here and we're moving down this upper triangular, finding the ones, the green ones, and swapping them out, moving them down into the lower triangular in some pattern, some manner we're doing that. So let's see, we've got 19 and 14 here. Is that the next one we look at? And we did 14 and 17. Okay, but there's a number of things to choose from as we go through. Now this one right here, we got 19 and 14. Let's look at that. That's 19 and 14. So we have no green up here in the upper triangular portion. We're actually moving them all down into the lower triangular portion. Okay. So what we've done is we've gone through and moved everything down into the lower triangular portion, and once we have it down there, then we do the inference operation. So when we get this inferred data in blue, and here's the inference steps. This is basically put together as a proof of concept by Warfield, and you create a matrix D from the empirical data, create an identity matrix, you create M by adding D and I together, and then using Boolean operators. This is kind of a key part of this operation, is to use Boolean operators on a binary matrix. And in the initial work in selecting the math package for this, we decided to do a transform that allowed us to transform from decimal to Boolean. But these Boolean operators are very important, and then we multiply those out until they don't change anymore. That's our additional inferred ones. And then we add all those additional data points to the matrix are inferred. And of course this whole process is clearly defined in Warfield's work in Societal Systems on page 230. So here's our original empirical data, and this of course is the identity matrix over here. Then we add them together and multiply them until they don't change, and this gives us our additional inferred data points. So we subtract the D from the M, and whatever's left over in ones are the inferred data points. And this is the decimal to Boolean mapping. This is all in the SAGE worksheet for this week. It explains in detail how this particular function works out. So our general process check for right now, we've gone through and we've identified the cities, we've collected and entered the empirical data, analyzed and ordered the cities, and we've conducted an inference analysis. So we're going to go on to the next steps. Now we collect more empirical data. You can see we have more green up here in the ones. And we walk through and move those down. You see there's no, you're going to find these green ones. So this is, that looks to be 10 and 8. That's right. So now the next one seems to be 15 and 10. Right, next one is 5 and 9. So you can see we're going through 4 and 5. And then 10 and 4. We're going through and we're walking down this way on the upper triangular, taking all of these and moving them into the lower triangular. It was 9 and 10. The next one is 5 and 9. And then the last one is 9 and 18. Now we have everything in the lower triangular. So the ordering process that we just went through, and one of the things that we can do to look at this is we take the final marking space of all ordered data, and we create a value space. Then we create an outcome space by multiplying the final marking space times the value space. And the multiplication in this particular case is cell by cell multiplication. And then we observe the pattern in the outcome matrix. We sum each of these rows, and then we look at this and we sum those up, and these row sum numbers may be used as a guide by the computer or any other process to identify the rows to swap. So let's look at this. This, again, when we're all done with this and it's all ordered, we're going to have all the ones in the bottom. So this is all the ones in the bottom, all the zeros in the top. This will be the final configuration. This is our value matrix that we've come up with. We multiply these two together, we get the outcome matrix here, and then we add up the rows for each one of these. We have our row sums over here. So there's going to be no ones in the top because there's going to be one city that has nothing north of it. Okay, and so we then take and run the inference operation again and get more blue ones in our lower triangular. And this is the same inference process steps that we did before. And this is the numbers and the matrices for this particular operation. And of course you do the same decimal to Boolean transform as we did in the previous operation. So what we've done is we've gone through and completed these first 7 steps. We've identified the cities, we've collected empirical data, we've analyzed and ordered the cities. Now this is the operation that we're looking at to computerize, and then we conducted the inference analysis, then we did it again. And now next videos we're going to go through and look at these last 2 operations and do those in more detail.